Okay, it looks like it's going live. So just kind of reminding you of what I was just talking about. I'm going to use these terms V peak to peak, V peak, and VRMS probably a lot today. To be clear, the maximum is the amplitude. So V max is equal to V peak. It's the amplitude. That's the height of the wave. So watch for that today. Okay. I'm going to use those terms interchangeably. I can't help it. I don't mean to. Now, another thing that you might see me do today, omega naught and omega res. Those are the resonant frequency. If you recall, does anybody know the equation to how to get that? Do you remember it? 1 over
square root of LC.
Hold on.
Yeah, you got it. Square root of LC.
Omega.
There we go.
Just give me 1 second. Resonance, which is equal to 1 over.
If you get a chance, Nick, could you hit mute?
Oh, I'm sorry.
No,
so
it's cool.
sorry.
It's cool. No, it's not a problem at all. Not a big deal. I don't care. So is everybody cool that these are kind of our basic formulas today? All right. So now let's just pick some random numbers. How about we do, well, let's do 555. And then a typical one of these might be 3.33 millas, which I don't know if you recognize that. And then this one, let's just say it's, how about 1 E negative 6? So that's 1 micro. All right. So, and if you like, you could even do this 3.33 E negative 3. So a lot of times it's handy to do scientific notation in here. And I'm just going to center these so I don't have to look at them. Oh, I can't help it. Let's just quickly make this a subscript. All right, there we go. All right, and so what are we going to do today? You're going to see the frequency in hertz change. So notice what I do to get this formatted quickly. I always type it without any formatting and then do the formatting right afterwards. If you try to format as you go, it's usually slower. Now we might need omega, which is in radians per second. And you know what I'm going to do? I'm actually going to do kilohertz and crads. So if I want omega, I'll just go into here, symbol, and then we'll do control I. Got it. There's my omega. Now, what are some things that we might plot? There's X subscript L, and I'm going to stop formatting now. Oh, maybe not. We'll just do this right. So hopefully you're following along okay, and this is not wasting your time. Oops. Oh, there we go. So the idea here, oh, and then maybe we want to plot I max. Let's just do this. It's probably going to be milliamps, but I don't know. All right, and so let's say we've got this, and this is what we're trying to plot today, okay? And maybe we want to get the phase angle. All right. And so these are the things that we might want to do. You could look up the symbol phi later. All right. So let's just say we start here at 0.01, 0.02, 0.05, and then I'm just going to hit equals times 10. And then I'll just fill this down till I'm blue in the face. All right, and so let's maybe stop up here. This looks like it would be 1 million. All right, so we probably, actually, we don't need that much. Let's go to 1,000, because that would be 1 million, right? Because it's 1,000 kilohertz. And I also can't see it on the page, so let me shrink it down just a little bit. All right. So again, this would be what? 0.01 kilos, so I think that's 10 hertz. This would be 100 hertz, 1 kilo, 10 kilo, 100 kilo, 1 mega. Now, notice why I'm doing this. We're going to go over a huge range of frequencies, and killas, normally we wouldn't do this with this prefix, but because we're going over such a huge range of frequencies, this will be useful. Somebody tell me, I need omega. How can I get omega from F? Remind me.
Isn't it 2 pi times the frequency?
So remember, if you want to use pi in Excel, you got to put the parens on it. All right. And so because I used kilohertz here, I end up with kilorads. Now, all right. All right, so let's go ahead and keep going here. Actually, you know what? I'm going to take these killas out, and you'll see why. You may want to use them today, but to be honest, it might be easier if you have no prefixes when you first do everything, okay? So even if they look big and ugly, you can clean it up later. The idea is if I put prefixes on these numbers, I'm going to have to think a lot when I do these 3 calculations here. So actually, I'm going to take off all the prefixes right now, and then you can always make extra columns of data with better prefixes later. So let's go ahead and crank this out. And then actually, we probably want to start this. I'm going to start this at a different number now, 10, 20, 50. And so that'll fix it up. And the numbers don't matter that much. You're going to do your own numbers here, something later. Okay, so there's some different frequencies we have. Okay, somebody remind me, other than Nick, how do you get X subscript L?
It's omega times L.
Equals omega times L. So what should I do right now?
Press enter.
Dollar signs first.
Ah, yes.
Oops. Ah, I clicked the wrong spot. So I'm going to click L. Remember, L is a constant. Don't forget to hit those dollar signs. There we go. Looks like it's doing scientific notation. It doesn't really matter. Who cares? We can clean it up later. Somebody else. So we've had Nick, we've had Trey, somebody else. How do I get X subscript C, the capacitive reactance?
1 over omega times C.
Yep. So I'm going to do 1 over omega over C, right? That's the same thing, agreed? And then what do I need to do before I fill down?
F4.
Exactly. And look at the values. Does this make sense with what we were just talking about? At low frequencies, these are tiny numbers. There's small powers of 10. At low frequencies, the capacitor has large powers of 10. The opposite is true down here. Does anybody remember the equation for Z? I'm going to write this on the screen. Oh, go ahead, somebody. What's the chat? Oh, it's all right, Nick. Not a problem. Does anybody remember how to get Z? What was the equation? Can you tell it back to me?
If we've already answered something, can we answer?
Yeah, go for it. What the hell?
It's the square root of r squared plus xc minus xl. I can't remember which one was first.
It's usually XL minus XC, but
Oh, okay.
Does it matter?
No.
But it will matter for the next thing. And so you want to remember Eli, ice. Yeah, anyway. All right, whatever. We'll go with the inductor. All right, so code that in, everybody. Code that in right there. It's not that bad, right? I'll do it in just a second. I got to get rid of my annotation. Help me out. What's the formula here? I guess there's a square root. Square root of, what do I do? Which cell? So somebody knew this time.
A2.
A2. Do I need dollar signs? Yes or no?
Yes.
Yes, because it's a constant. And then square it. Good. Plus, I'm just putting in all the parentheses. So now somebody else here. What cell goes next?
C5.
What was it? I couldn't hear you.
C5.
C5, yep. Do I need dollar signs? Yes or no?
Yes.
No, because C5 is going to change with the frequency. Do you see that?
Oh, okay.
So that's what I wanted to point out here is that some of the things change and some of them won't. R is a fixed value, L and C, but X sub L depends on the frequency. So as we sweep the frequency, as we change the frequency or sweep it, that one will change. All right, so then what's next? Claudia, you want to just go ahead and finish it off?
Yeah. Is it D5?
D5. There we go. And so now we've got our Z value. Notice Z is really big. Now, take a guess. Look at this column of data that I just highlighted in red. Can you tell what the resonance frequency is approximately? I can. Maybe if I reduce the number of sig figs, I want you to see this in the data. Which number is almost exactly equal to the resonance frequency? So obviously, here's your frequencies over here in blue. Right. Let me get them in blue right now. Which of those blue frequencies in the first column in column A happens to be closest to the resonance frequency? Anybody?
5,000.
Let's see. You said 500's pretty close. I think
2000.
2000 is close. Remember, Z equals R at resonance, right? How could we check? How could I figure out the resonance? Well, we could do let's calculate it. How do I calculate the resonance frequency? Remember, numbers are not italicized in a subscript or superscript. What's the formula for getting the resonance frequency? Does anybody? How would I type it in terms of this Excel?
Is it the 1 over the square root of L times C?
Yeah, so in terms of this spreadsheet, what do I need to click?
B2 and C2?
Do I need dollar signs?
Yes.
You don't
Since you're not
need
making
them.
a column, you don't need to.
You don't need them, but we could do them, and maybe we should just as good practice to keep our constants with our dollar signs. So you don't need them. Now, wait a minute. This number does not look the same. If I get it out of scientific notation, that does not look like 2000. Is that a problem?
No, I
Why
actually just
not?
had that issue too, because we just calculated the angular frequency.
Exactly. So if we look at this, let me make that purple. So how could I get the actual, how could I get the linear frequency, F0, to compare this to? Ah! Well, now I know what letter phi is, huh? wait, what were we using? Cambria or Calibri? Oh, there we go. How do I get the linear resonant frequency? How do I get F naught instead of omega naught?
Divided by 2 pi.
Yeah. And notice divide by 2, divide by pi saves me some parentheses. And look at that. Notice that? So look at this. I'm going to get a little spicy on you guys. Looks pretty good. All right. So far, so good. How do I get the current amplitude? Remind me.
Isn't it just Vmax over XC?
Not XC. It's Vmax over
XL?
Nope, you're close.
Z.
Yes, Z includes contributions from both the inductor and the capacitor. So Z has got all of it put together. It also includes the resistance too, right? So Z includes the contributions from the capacitor, the inductor, and the resistor in terms of overall impedance. So it takes all the ohms from all the things impeding current flow. Is that good? So then, Sean, go ahead and tell me what I should type in.
D2 with dollar signs divided by E5.
And notice it's pretty small. So Sean, I'm going to pick on you a little bit. What if I want to convert these to milliamps? What would I need to do to my formula?
F5 times 1,000.
Yep. So just to put these in milliamps so that's easier to see. Now let's get rid of some of these sig figs so it's not so obnoxious. Now let's plot this. F, well, usually you want to plot omega versus I, right? Or omega versus Z. So if we insert this, notice it looks nothing like what I told you it does, right? Here's why. These plots go over such a huge range of frequencies, you can't see all the stuff below. Look at these numbers on the x-axis here. It starts out at, what is that, 100,000, I think? Or it starts out at 1 million or something. So if we want to see this better, right-click, Format Axis. Oh my gosh. There's a button right here that says Logarithmic Scale. I don't know if you can see it, but can everybody see where my mouse is? I hope you can. Let me, right there. There's a thing that says Logarithmic Scale. If you click that, you can see it much better. And it looks like what we expected. There's a peak, right? The current amplitude peaks at some value. Got it? Let's see what it looks like if we plot F versus Z. So, oh, by the way, if you don't know how to do this, remember your columns are not next to each other. You could do F, highlight that. Now my hands are off the keyboard. I haven't done anything. Now press and hold Control. Press and hold Control and highlight the Z values, right? If you insert this one, oh, I lost my plot. Insert, plot. Now notice, this does not look anything like it. What do I need to do right away?
Logarithmic scale.
Yep. And that's what we expected. It's very large at high frequencies. It's very large at low frequencies. And it's basically, what is this value on the x-axis here? If I want to see this a little bit better, I could change my maximum to say 10,000. How about let's go 1,500. And notice what value does it bottom out at? Huh. Microsoft. It bottoms out
580 something. Like
so yeah, it's 555. Right? The value of R, remember?
Yeah.
The minimum value of Z is the resistance. Is this helping you guys get a feeling for this, or is this wasting your time? Is this good or bad?
Good.
Good? All right. Now let's do one last thing here. Phase angles. Gosh, I'm running out of room with this crap written all over my screen. Can I clear this crap out? I have to.
You could probably clear that.
All right. So I need to explain to you about phase angles really quick. So the idea here is, what is a phase angle? There's going to be a curve. Now I'm going to try and use the same colors that are on your O-scope. I believe it said yellow is going to be channel 1, which is V of the source. Apologies for the colors. I'm just trying to use the same ones that the computer was using. Now the current, I think, was going to be, they may not be the same size, and sorry, they're not, but we see that they don't peak at the same time, and that's what I wanted to point out. Now, this obviously is some sort of time measurement, okay? But it's equivalent to a fraction of the period. The period would be from right here all the way over to right here. That would be the period, right? So in this case, it turns out if I take the ratio of the time over the period, that should equal the amount of phase angle out of 360 degrees. Think about this now. What does this mean? The period is a full cycle. A full cycle is equivalent to 360 degrees. This is the amount of offset. This is the phase angle. The phase angle is like the offset. So the phase angle relates to these. In theory, this is how you get the phase angle. The impedance is this leg of a triangle. This is the phase angle. This side is XL minus XC. I can explain why later, but this all relates to complex number theory. And this side is the resistance. So notice, give me an equation that relates to the phase angle and SOHCAHTOA. Give me a formula, people. Anybody, try it. It's okay to be wrong.
Cosine phi is equal to R over Z.
Okay, that is a very good one and a common one. Cosine phi is so common in these, that's often called the power factor. We'll discuss that when we start doing problems later. But so that is one valid one. It turns out I don't like to use that one. So give me another one.
My book says cotangent of XL minus XC over R. Arctan.
Yes, in tan inverse. So yes, this is the one that's classic when you're first starting. So, and I want to use this because this one helps us understand the minus signs. I want to point out here, you'll never see a minus sign with this formula. And so it turns out the cosine is great for doing power calculations, Trey, but it's not good for getting the plus minus signs. Because if you take cosine inverse of this, you can't tell if the triangle is this way or that way. And so you can't tell if you have a positive or a negative angle. So it's not that what Trey said is wrong. It's just really difficult to use in practice to get the sign of the phase angle. It's great for power calculations. So let me write the one up that Eston just chose. God, I can't believe I have to say Eston picked something nice. Oh man, that hurts my soul.
Yeah.
So, I'm just messing with you, dude. All right, trying to have a little fun. And so, Nick, now this is why we'd better get it right. And this is why I want you to be in the habit of always saying XL minus XC over R. And then, this is kind of, I'm running into the room here. Let me erase that Z and move it down. Sorry. Okay. So that's the, this is called the phase angle triangle. There's two different ones. We'll talk about it later. But so let's go ahead and pop this in. Okay. So it's equal to a tan of, help me out, somebody. I mean, I'm doing it all for you. You might as well tell me what to type.
Another set of parentheses.
All right.
And let's see. C5 minus C6, or D5. And then all of that divided by, where's it at? R, which is up there. You have to convert it to, that's currently in radians.
So what do I do?
Type in degrees and then put all of that in parentheses.
Now, and notice, I think you agree right now, this is better than radians. Even though it's a bit of a pain in the ass, people understand degrees. So let's take a look what this looks like. Oh, let's do omega. Let's try and be legit here. Predict what you think it'll look like, everybody. This one's kind of spicy, it turns out. Whoops. This looks like shit. I can't see anything. What do I need to do?
Make the graph like be logarithmic.
Yep. I'm telling you, this is great stuff. I hope this is helping you. Isn't that interesting? You get this little curve in there, and I've seen this. Now, you could try and do this with more data points or use a linear scale and see if you can get rid of that curve. But I think what you'll find is you usually get some of this waviness no matter what you do. But so notice the phase angle. Now, here's a tip, people. Remember Eli, the ice organism, right? You're supposed to be tested on this, and then we'll let you go. So Eli, E is like the source voltage, and I is like the resistor voltage, because I is equal to voltage across the resistor divided by resistance. Now, wait. Don't I mean I max? Yes. All right. And don't I mean R VR max, or you could call it peak? I thought I told you earlier that I was equal to V max over Z. Which one is it?
It's the right one if you're at the resonance frequency, right?
It's both of them all the time.
Okay.
The trick is, look carefully. This was voltage of the source. So there are two ways to get the current amplitude, people. Listen carefully. This is what confuses most people in lab today. This is a way to get the theoretical voltage of the theoretical current. You take the source voltage and divide it by Z. in practice, in the experiment, what you do is you take the resistor voltage, not the source voltage, the resistor voltage, and divide it by R. If you are an electrical engineer, this should be something you never, ever, ever forget. If you need current in a circuit, put a frickin' resistor in there and measure its voltage, and you can experimentally get the current. This is how you theoretically get the current.